So I welcome Professor Christian Maes from Leuven University, where I also happen to spend around 3 years. And I actually met you in your own office some 30 years back. Welcome to the conference. We are happy that you join us, and maybe Senor Schlossman somewhere also in your office, or maybe not, but we had
no, he's not so far from here. He's not so far from here, but not in my office.
Oh, we can start on time.
Okay, wonderful.
So welcome.
Just tell me if I can start. It's fine.
I suggest that you can start. We are all online and on site.
Wonderful. So,
thank you.
Thanks a lot for the kind invitation, so I can be at least somewhat present at this conference dedicated to Vadim MALYSHEV, who has indeed also visited Leuven a couple of times, and I have been very often amazed by the depth of his thoughts and also about the creativity in which he was searching for new applications in various domains where probability theory and discrete mathematics often played an important role. But also, and that's also why I put here the M union phi, the union between mathematics and physics, because he also, I believe, worked in a tradition where physics is a very good inspiration for interesting mathematics. Okay, so in the 30 minutes, I will say something about the third law. The third law is, in fact, something which goes back to hardcore thermodynamics, in particular Nernst, who got the Nobel Prize about 100 years ago, related to his study of low temperature specific heat. And so 100 years later, we published a paper in Journal of Chemical Physics about the Nernst heat theorem, but for non-equilibrium jump processes, and the mathematical version is still under revision. And but you can find the version here on the archive. So this is very much work in collaboration with Karl Netočný from Prague and Fase Kodabandelu, who is a graduate student here in Leuven. Okay, since I have not so much time, I suppose that I will spend like 10 years to explain what is an extended third law, then 10 minutes for what are the models, and 10 minutes for the statement, basically, and the idea of the proof. But more specifically, I have to tell you what is a non-equilibrium specific heat, because this extended third law will exactly say that this, or at least some part of it, is that non-equilibrium specific heat is going to zero at zero temperature. And that I will try to explain for Markov jump processes. Basically, I will give two examples, which are driven lattice gases and a two-temperature easing type model. And then at the end, I hope there is time to go to the ideas of the proof. Okay, so if there's something not clear or you want to interrupt me, of course, you're very welcome at any time. Otherwise, I just continue. And let me just, by historical introduction, invite you to look at this diagram. So here we see for a number of solids, lead, aluminum, how the heat capacity behaves as a function in the horizontal axis of the absolute temperature. Now, you see, important characteristic is that at high enough temperature, it depends a bit on the system, they more or less all follow the same value for the heat capacity, which is dictated by a law which was originally experimentally or phenomenologically related to equipartition theorem also, which is the 3R Dulong-Petit law. But then, on the other hand, if you go to low temperature, they all go to zero. You see the heat capacity goes to zero. And since a long time, already in the 19th century, much before all the experimental problems were reported related to black body radiation or photoelectric effect, people worried about that. Maxwell already in the 1860s saying we have a wonderful molecular theory, but we don't understand heat capacities. And it was really only by the work of mostly Einstein at the Solvay conference of 1911, and then much more experimental work, that people understood why it could be that this entropy or specific heat is going to zero at absolute zero. I will not discuss that in thermodynamic language. I refer to the book by Herbert Cullen, both for history and thermodynamic precision of what this exactly means. For people who are interested, at least in the equilibrium statistical mechanics, so the standard version for the third law in statistical mechanics of equilibrium systems, I think you should look at the paper in Journal of Statistical Physics of 81, where general considerations are combined with classes of examples to understand the conditions under which indeed and in what sense the entropy density for a bulk system goes to zero at absolute zero. One should say, however, that it's not like the first law or the second law. The third law is not a law in the sense that there are exceptions, there are counterexamples. It's not built within the framework of statistical mechanics. There are counterexamples already. Pauling in 1935 had these dimer models or ice models rather. And also this has been continued with spin ice. But about all these things in equilibrium, I will not speak. I don't have time, and I want to go to non-equilibrium. Okay, so first of all, a general drawing here or a picture from Escher to bring you in the spirit of what it means to be in non-equilibrium. So by non-equilibrium, I mean steady non-equilibrium. So I'm not speaking about relaxation to a stationary distribution, or I do not speak about relaxation, transience to an equilibrium. No, I speak about a driven or an active systems, which, okay, is modeled on the short time scales that we are in a stationary regime for the system. It's often, or mostly, it's always an open system, and it is a non-equilibrium steady state. And one of the important things about these non-equilibrium systems is that it's not just determined by energy entropy balances. There are many other things that start to play a role, and that's what we want to discover in non-equilibrium statistical mechanics. You see, normally in equilibrium systems, say the energy gives you a kind of a ladder. You have a scale of energies, and if you go from higher energy to lower energy, you will emit heat or you will emit radiation of some sort. In this non-equilibrium system, it's not because, okay, forgive me, maybe the metaphor with Escher here, it's not because you're higher, here, for example, higher than here, that it is not possible that water is flowing from lower to higher. So this is the world of Escher, this is the world of steady non-equilibrium. It's full of pumps, it's full of active processes, it's full of driving, and it is in that context that I like to speak about the heat capacity. Okay, so take your, I will now tell you what I mean by a non-equilibrium heat capacity. It will include, that's also why I didn't do it yet, it will include, of course, the notion of equilibrium heat capacity. So take your favorite samovar. Maybe it's not a samovar from Tula, but anyhow, it's a device that basically works here from doing work by a battery. So it pumps a current through a resistor. And you know that if you do that, this is a dissipative element, so it will produce heat. And that's the way you make hot water for tea. So this is the direct conversion, if you wish, which is a complicated process. I'm not going to speak about that. The conversion of that work into heat, the so-called Joule heat. And of course, you can use that to make hot water. But now let us imagine that in fact, this reservoir of water is extremely large. Still, this Joule heating will going on, but the temperature will hardly change. So there is Joule heating, but basically we can imagine a limit where it is fixed temperature. Okay, now let us do the following. So we have a certain dissipated power, that is this heat which is emitted per unit time in the water or in the surrounding environment. And that, you can imagine, also depends in fact on the temperature of the neighborhood. So what happens now if I change the temperature? So maybe not experimentally, but think of a thought experiment where I'm doing this change of temperature. So then before time zero, we have a certain positive dissipated power, that is this blue line here. And if we change at time 0, say some parameters, but in particular we make a change in temperature, I'm speaking heuristically for the moment, then at a much later time, we can imagine that we are, I hope you see my cursor, that we are again having some power at a new temperature. So we go from one non-equilibrium steady state to a new non-equilibrium state. And there is a transient of a relaxation from one non-equilibrium to a non-equilibrium. And this shaded area here, you see this shaded area, well, will be basically proportional to that change. So let me call that change dt, the change in temperature. Then this area here will be some constant multiplied with dt. Well, that constant, that's called the non-equilibrium heat capacity. Okay, so if you are in equilibrium, then you should imagine, well, it's true that these two blue lines here at asymptotically to the left and to the right, they are just at 0. There is no dissipated power in equilibrium on the average. But nevertheless, if you change a parameter, you change temperature, for example, there will be a bump and then goes down. And that bump, that area adds the heat capacity. So the heat capacity is an intermediary between the heat and the temperature change. That's how you should think about it. So that shaded area we often call excess heat, because it's the heat which is entirely due to the relaxation. It's not, there is always a background, which is sometimes called the housekeeping heat, this Joule heating. It's a housekeeping heat, but then on top of that, because of the change of parameters, you have an excess heat, and the measure of that is taken via the heat capacity if you change the temperature. That is what we call heat capacity. So that is the history, that's the physics interpretation. I hope that's more or less intuitive, clear, but let me now make it a bit more formal and specific in a very simple model. And the choice I'm making is a Markov jump process. And it's not an accident that I'm taking a Markov jump process, but later about that later I will explain. So we consider a connected finite graph, so finite irreducible setup, where I have vertex sets and I have edges. The vertices I call states, but for physics purposes, these states, they could be energy levels, or they could be many body configurations. Anyway, there are states. And then there are edges between states, and okay, where they come from, let me not speak, but there will be, for the jumps, there will be a transition rate, and I will denote it by kxy for a random walker to hop on that graph from the vertex x to the vertex y. So the kxy are simply the transition rates for my Markov jump process, which is just a random walker, but not a simple random walker on the vertices. So here is my graph, a simple graph. Maybe there are loops. Anyway, I can look at the only transitions, and they are always non-zero. When there is an edge between x and y, I have a possible transition, and I have then also a double possibility. For every edge I have, you can go from x to y, or you can go from y to x. That is what you should imagine. And the position of the random walker at time t, I just denote by xt, is somewhere in the vertices. So that's a very simple setup, I believe, to start the problem. So just because of the irreducibility of the graph and Markov jump process, we have a unique stationary probability distribution, and I denote it by rho s. The S stands for stationary. It's a solution of what is called a master equation. This L dagger here, that's the forward Kolmogorov generator, but never mind about that. So it's just some notation. We will denote the brackets with an S. That's just the expectation of a function on the vertices in the stationary distribution. And the expectation at time t, when you start in a particular vertex, that is given by the semigroup acting on F. The semigroup is the exponential of the time t times the backward generator. Okay. So just to be sure, again, we speak about stationary probabilities. We do not speak about equilibrium probabilities. We make a difference just to make a useful difference between equilibrium and non-equilibrium. More in particular, let me skip for the moment the fact that we have parameters, but if we take the ratio, the kxy over the kyx, when you have an edge, both numbers are positive, we take the logarithmic ratio under detailed balance. for which we will have reversibility, a reversible stationary process, this can be always written as for every xy, sorry, there is a potential or an energy function, so that for every edge we will have that this is just the difference of that potential. So that's detailed balance, and I refer to that as an equilibrium dynamics, and then the stationary measure I call the equilibrium measure. Okay, so that's a bit of notation or terminology just to make precise what I mean. So let us go back now. So we will have parameters. So we will have that the transition rates, and as a consequence, the stationary distribution will depend on parameters. And in fact, there are two types of parameters here. There is the inverse temperature beta, and there are other parameters that perhaps we want to specify or not, but it could, for example, be that the energy depends on these parameters. This 1 over kBT, Kb Boltzmann constant T temperature, this 1 over this temperature, that's what we call beta. So detailed balance is to say that the logarithm of the forward and the backward transition can be basically given as a change in energy. Okay, so here now to make connection with thermal physics, that's where the frog jumps into the pool, we will identify more generally the heat to the environment during a transition as this logarithmic ratio, but we no longer require that this is the difference of a potential. Okay, so this will be an antisymmetric function under the exchange of xy, and this function does not depend on beta, but there may be a prefactor which is beta here. So that is how we define heat. That is called the condition, I mean, this interpretation of this condition that does not depend on beta, and so that's called local detail balance. And for a review, there is a kind of a review for inside post physics 2 years ago that I wrote to understand heuristically where that comes from in a certain V coupling limit, if you care to know about that. But anyhow, so here is the setup. We have the ratio of transition rates, and there is associated to that a heat, and that heat flows to the environment. Okay, so then here comes 2 or 3 more formulas, and then we're finished. So the heat in the non-equilibrium dynamics, which is this Joule heating basically, that is associated with the logarithm of that ratio. So think of the Q alpha xy, this antisymmetric function here. Then we have the expected heat flux is obtained by multiplying that heat with the transition rate and summing over y. That's called the expected heat flux when in state x. And it has a stationary value, which is always non-negative, which is easy to prove by convexity, basically. So I repeat, we start from the notion of heat via the transition rates. We look at the expected heat flux when you are in x. What do you expect will be the heat to the environment? And there is also a stationary heat. So we don't need any more definitions than that. So these are the 3 notations that I hope you kind of remember. So I remember the Qxy, that's the heat which is going to the environment in the transition when the walker jumps from x to y. There is the expected heat flux, which is this heat, but then taken, multiplied with this transition rate, and then there is the stationary heat flux. Okay, now, what I will do now is I do the quasi-static transformation. So what does it mean? I have these parameters which are beta and alpha in general, and they will undergo, I will have a protocol for changing them. So there is a certain curve here in that parameter space, but I will set up a quasi-static process in the sense that the time is multiplied with epsilon, very small parameter. And I consider such a curve, which is going to be a curve in that parameter space where the parameters are changing very slowly. And then I can look at 2 things. I can look at the time-dependent probability for finite epsilon. So I just solve the Maes equation, and I look at this probability, the time-dependent probability at each time t under that process. And there is the instantaneous stationary probability, namely take that parameter at that time, and for that to look at the stationary probability. So what I mean now by the excess, so we have an excess heat. So here is this, you remember, this was this was the expected heat flux. And I look at it instantaneously, I mean, for the time-dependent process, and that is for the instantaneous probability. So this is doing that if I integrate over time, this is really doing that shaded area. So the excess heat is in this Markov jump process defined like that. I just take this area is defined in that way by looking at the difference all the time at each moment between the time-dependent probabilities and the instantaneously stationary probability weighted with the heat flux. And that gives me the excess heat. And here is the first proposition, namely this excess heat, is epsilon going to 0, is becoming geometric. It means it only depends on the path, and it is invariant under a diffeomorphism, a rate of, changing the speed along which you go to the path. And it actually can be written in terms of the so-called quasi-potential, and the quasi-potential is defined here. It is a time integral of, again, an excess, a difference between the expected heat flux at time t, when you're starting at x, and the stationary one. So that's the first proposition, namely this excess heat gives rise to something which is geometric. This is related to a Berry phase, you could say.
Sorry, Christian, S there stands for stationary.
The S stands for stationary, yes. If I do a superscript in the bracket, it means stationary expectation. Yes. So I see, this is a converging integral, because this is like the expected heat flux at time t when I start at x. This converges exponentially fast and uniformly fast for every irreducible Markov jump process to the stationary value. So this is a converging integral, and that defines the quasi-potential. And it turns out that that quasi-potential is governing the excess heat in the way that in the excess heat, in the quasi-static limit, you obtain that the curve is in parameter space, where the integrand is basically looking at how this excess heat changes with the parameter. Okay, when all is said and done, we get that this excess heat infinitesimally is given by this, there is an S missing here, sorry. This expectation here must be in the stationary distribution. But the point is that this quasi-potential, which is playing a central role for us, is the solution of a Poisson equation. So it solves for here we have the backward generator acting on V lambda is given by a certain centralized function on the vertices. And the centralized function is the expected heat flux subtracted with its stationary value. So we have a simple Poisson equation in this Markov jump process, and we are looking to find a solution. The V lambda is the unknown, which has to have 0 stationary value. So that's the mathematical problem that arises. And if you find that quasi-potential, the heat capacity, the non-equilibrium, but also the equilibrium heat capacity, is the expectation of the derivative with respect to beta, the inverse temperature of this quasi-potential. So what is the algorithm? The algorithm is you have a certain expected flux. It depends on parameters. You look at it, the corresponding Poisson equation, to find the quasi-potential. And this quasi-potential, when you take derivatives with respect to temperature, basically, gives you the heat capacity. That's the algorithm to find non-equilibrium heat capacities. And if you are caring about detailed balance, or what I call the equilibrium dynamics, there is no stationary heat flux. There, the expected heat flux is in fact itself the generator acting on the energy function. And it turns out that the quasi-potential is basically exactly equal to the energy. So the quasi-potential becomes equal to the potential. And hence the heat capacity becomes just equal to the usual formula that perhaps you remember from high school. The usual heat capacity is the derivative of the energy, stationary energy, with respect to temperature. So that formula is an extension to non-equilibrium from the usual equilibrium thermodynamics. And as I said, in equilibrium, the quasi-potential is exactly equal to the energy, centralized. But in general, in non-equilibrium, we have to calculate that heat, that quasi-potential from a Poisson equation, where now, well, there is some non-trivial things happening.
I'm sorry, Christian, stupid question. What is beta? dV over d beta?
Beta is the inverse temperature, so it means the following.
But in the equation, for in the definition, there is no beta. Or is there?
Hold on a second. So as I said, that the parameters contain a beta. So there are two parameters. There is a beta and there is other parameters.
Lambda is
the
beta
beta
alpha.
enters
Okay.
here. Namely,
Okay.
beta is such that if I multiply, if I take the logarithmic ratio, it's equal to beta times some function, which does not depend on beta.
Okay.
I mean, of course, in models, you will immediately recognize what is beta. So maybe in the examples, you will understand better. But there is a beta around. You see, we always like to take non-equilibrium systems for which we can have a reference in equilibrium. So we have a reference equilibrium where I have an environment at a certain temperature, and then we perturb it in the non-equilibrium regime.
Okay.
Maybe I'll go to a specific example immediately to make that a bit clearer before I go anything else. So here, let's look at that picture here quickly. So we have an exclusion, asymmetric exclusion process on the ring, but asymmetric exclusion process also has birth and deaths. So these stations that you see here, these are somehow, this is a drawing of a birth and death process that you have. And when you have a particle in the station, then the particle is typically driven clockwise. And so we get here an asymmetric exclusion process, but the particles can die or can exit or can be born at each station. Okay, so it means that I have the dynamics has two parts. I have a hopping dynamics. And for example, here the non-equilibrium parameter is zeta. Zeta is the work done by a driving force. So this creates a bias. So this is the asymmetry in the exclusion process. So this is the minus and the plus means here that there is a bias in the clockwise direction. If zeta is equal to 0, you see, if zeta is equal to 0, the forward and the clockwise and the counterclockwise are just constant, the same number, but the zeta introduces a bias. That's the asymmetry in the exclusion. And then we have also the birth and death process. This is parameters alpha and delta. And we also introduce a barrier for dying and for being born, which we denote by delta, and also that is multiplied with beta. So you see here, we have beta multiplying this work, and here beta multiplying this energy barrier. That's the two places where here we find the beta. If zeta is equal to 0, we have detail balance. If zeta is not equal to 0, we don't have detail balance, and we go to a stationary distribution, but it's a non-equilibrium one. It's not reversible. And here we have computed the heat capacity, and okay, you see plots here. In fact, here it's possible to, in the thermodynamic limit, so n going to infinity, we speak about a specific heat, to calculate a specific heat exactly. And I don't want to discuss too much about this because time is going very fast. But the first term is basically just the expression you would get in equilibrium. So when zeta is equal to 0, you just have a two-level system. So this is basically the heat capacity for a two-level system. And the non-equilibrium parameter zeta enters with zeta squared for small zeta. And it introduces a lot of kinetics. For example, the kinetic barrier is there in this expression of heat capacity, which is absolutely not relevant for the equilibrium heat capacity. So the chemical potential enters and the kinetic barrier enters, which are invisible. If you look, for example, to the graph in temperature, you will find that there is a giant magnification of heat capacity at low temperature, but nevertheless, all the heat capacities, even in non-equilibrium, they go to 0. So in that sense, we speak about an extended third law. The heat capacities do go to 0. And the question is why? Because we can no longer use entropies. There is no entropy anymore. We cannot use Nernst law. It's not equilibrium thermodynamics. The question is, why do heat capacities out of equilibrium go to 0? That's the question of the talk. Okay. So another example, but okay, I have no time to discuss it, but take a particular, say, spins, magnetic easing model type of thing, and you can alternate between two temperatures. So you put it in the oven for some time, and then at random time, After an exponentially distributed time, you put it in the refrigerator, and then after an exponentially distributed random time, you put it again in the oven, and you do that alternating in random times. You will not get a detailed balance evolution. You will get an irreversible Markov process. And the question is, what is the heat capacity of this magnetic system? Okay, well, I don't have time to discuss it too much, but you see, we can again compute for this, at least in the Curie-Weiss limit, we can compute the heat capacities. And okay, I'm not going to take you through all of this formula, but one important thing that we discover is that the usual heat capacity in the Curie-Weiss model does not show a divergence. It's a discontinuity, but not a divergence at the critical point. But here in non-equilibrium, when you have temperatures which are different, you get, in fact, a critical exponent. So you get a divergence of the heat capacity. So that is picked up by the non-equilibrium heat capacity. If delta is the non-equilibrium parameter, if delta is equal to 0, you may wonder why there are now 4 heat capacities here, and that is because I have 2 temperatures. So I can change the temperature in one reservoir and see what is the difference in the heat flux to the second reservoir. So in that sense, the heat capacity has become a matrix. Okay, I will not say anything more of that, and I will also not give you more examples, but let me also show you here that, say, these are other examples of heat capacities. We always have, it goes to 0, but it can even become negative at low temperature, these heat capacities. And the reason is that in equilibrium, heat capacity is like the variance of the energy in the canonical ensemble. In non-equilibrium, the heat capacity becomes a covariance between the quasi-potential and basically the Boltzmann entropy type of thing. And so because the Clausius and the Boltzmann entropy are no longer the same for non-equilibrium systems, you may end up with negative correlations between them, and that is the negative heat capacity that you see here. Anyway, that's not the subject of my talk. The subject of my talk is, why does that go to 0, these heat capacities? Okay, so basically on the mathematical side, the main thing that one has to prove is that the solution of the Poisson equation remains bounded as the temperature goes to 0. That's the mathematical thing that must be proven. Okay, to understand that, maybe I have to look at some formula. Okay, it all goes very fast, but the excess heat, you remember the excess heat was an expectation of a derivative of the quasi-potential. But some partial integration gives you that it is really, you can write it as the sum over the states of the quasi-potential multiplied with the change of the stationary density. So there are the proof of the heat cap of the Nernst postulate for non-equilibrium proceeds in 2 steps. You will prove that this nabla of the stationary heat density will go to 0 at 0 temperature, which is a non-degeneracy condition. But there is also now a new condition that you must prove, and that is that the quasi-potential goes to 0. That the quasi-potential remains bounded. So that goes to 0. This density here becomes, this nabla, the change of the stationary density goes to 0 at 0 temperature. But the quasi-potential must remain bounded, and that is highly non-trivial because you have to solve this, well, you have to understand how the solution of that Poisson equation remains bounded. So you have to have the uniform boundedness of this quasi-potential. Okay, so I will just end my 30 minutes more or less by not speaking about the statics. So I will not speak about the vanishing of this nabla of the stationary density, but I will just say 2 words about the uniform boundedness of the quasi-potential. And here the mathematical work really starts. I will not give you too much of okay, so there are basically 2 ways of approaching. One is, I'm not having time to discuss it, but there is something called the matrix forest theorem, which gives a graphical representation of the solution of the Poisson equation. And these you can use for asymptotic analysis for beta going to infinity. But maybe I will just end by mentioning that to show the boundedness of the quasi-potential, it's in fact sufficient to show the boundedness of the differences of the quasi-potential. And that means that you have an integral of a difference. Now, you see, the difference is that once here you start a random walker from X, and here you start a random walker for Y. So it invites, of course, coupling arguments. Clearly, you know, if you can couple the random walker starting from X to Y, then if they meet very fast, then this uniformly as the temperature goes to 0, you will get boundedness of this quasi-potential. So you can do that via a coupling argument. But another method, which is even more elegant, I find, is to go via, but is the same physics idea, is to go via the so-called, well, the mean first passage time or the mean first hitting time. So one proves that the difference in the quasi-potential can be written as an expectation in the stationary distribution of the expected heat flux, which is here. This would be a P, by the way, but then also a difference in the hitting times. The basic reason is that, you see, also the hitting times, the first hitting time is also a solution, is also a kind of Poisson, satisfying a Poisson equation. This is indeed the backward generator acting on the mean first passage or the mean hitting time of Z, and that must be equal to -1 for X different from Z. I think everybody knows this equation probably, so that is the understanding of the mean first passage time as a solution of a differential equation, basically. But this mean hitting time, this solution of this Poisson equation you can use to solve the Poisson equation of the quasi-potential, which means that you can plug in the difference of quasi-potential, the difference between mean hitting times, the first passage times. In other words, you can go to an upper bound, which I don't have here immediately, but basically the upper bound is you can express in terms of hitting times. So when you're able to estimate for neighbors what is the difference in hitting times, you will have an estimate on the quasi-potential differences, and you will have an estimate on the specific heat. It all goes a bit too fast.
I'm sorry. What is Q? Q of Z.
Q is our, I'm sorry, Q is the P that we had before. This is the heat flux, the expected heat flux in Z.
Okay.
So I'm sorry, the Q is what we call the P. So this is a statement here. This is a claim that the solution of the Poisson equation for V can be reduced to a solution, well, can be written in terms of the first hitting times. And the reason is because they are themselves solution of a Poisson equation, and then you can verify that they solve the Poisson equation for this mean hitting time. So in other words, from this mean hitting time, you can go to estimates and you can try to estimate the difference in the quasi-potential. And if you know the differences in quasi-potential, how they are bounded in temperature, by integration, you can go to the boundedness of the quasi-potential itself. And the boundedness of the quasi-potential is sufficient, together with non-degeneracy conditions of the static stationary distribution, to obtain finally that the stationary heat capacity for also non-equilibrium systems goes to 0. But there are conditions. I mean, just like in equilibrium, there are conditions, and there are also counterexamples. But maybe I do not have time. I think I'm over time already to discuss counterexamples. Okay, maybe I'll stop here and wait for some questions to see what I can do. Thank you. I do not hear anybody.
Thank you very much. Hello, questions?
I have a question about negative heat capacity. What is the qualitative difference between systems that possess this property and which doesn't?
Okay, so the negative heat capacity is impossible for equilibrium systems because,
yes,
let me go to the,
yes, that's true.
Just a second, let me go to this.
I'm sorry, may I ask one question? It seems
maybe more even.
Came again.
Sorry, we had some problem with the connection. Did you finish?
Yes, I thought. I'm sorry.
Okay. So the very last slide after this one, we
Okay,
we
so
were out of connection.
so I was trying to argue. I mean, did you understand that somehow an element of the proof? I was saying that the solution of okay, let me go back maybe a little bit. So mathematically, we have to understand the solution, which is so V we call the quasi-potential, and this is the solution of the following Poisson equation.
Yes.
You have the backward generator acting on that function. It's a function on the vertices, and it must be equal to some function, which of course has to have average or stationary average equal to 0, and the function is the expected heat flux.
Exactly.
Okay, so it's the usual Poisson equation. So the question is, can we take the inverse of this generator, right? And we
Yes.
can, in fact, because this has stationary measure 0. So, but it's not so easy to do that. I mean, it's kind of a very non-local thing that you have to control here in general. Okay. So the point is that you can have various representations of the solution of this Poisson equation. And one representation is via the matrix Forest theorem, which I have not discussed. Another representation is via hitting times. The reason is that the hitting times themselves, so tau yz is the mean first hitting time when you start in y to hit z. So that's the average of the infimum over all times of visiting z when starting in y. Okay, so this mean first hitting times, they solve themselves some kind of a Poisson equation. And the Poisson equation which they solve is equation 1 here. Namely, again, here you recognize again the backward generator acting on this mean first hitting time. But now we have another boundary condition, say, to that differential equation. And you can use this mean first hitting time to solve, to find the difference in quasi-potentials. And so now you have reduced the question of boundedness of quasi-potentials to a boundedness of mean first hitting times. Okay. And then, of course, there are other estimates which are needed, but okay, that I have not been explaining too well, but it's very natural somehow that you have to have a coupling argument, because the difference in quasi-potentials is a difference of two expectations, where I have an accumulated heat, but started from x respectively y. So when I am able to couple two random walkers, x and y, and they meet fast enough, depending on the temperature, even for very low temperature, then I can really estimate it in terms of mean. I mean, then those quasi-potential differences will be bounded. So that's why the physics or the heuristic reason of the first law is that you should not have a localization in energy. In fact, you should have what we call that the relaxation times should all be smaller than the dissipation time. But okay, that is words which come out of the mathematics, but I did not explain. But Valia had a question about the negativity of the heat capacity, and I'm trying to find a formula for you, which is this one. So I told you that the heat capacity can be written in terms of the quasi-potential in this way. But there is another representation as a covariance. So this thing is a covariance between the quasi-potential and the derivative of the logarithm of the stationary distribution. So in equilibrium, this is just the energy.
Yes.
In equilibrium, the quasi-potential is just the energy, and you get a variance. So that's why you get positivity of the heat capacity in equilibrium, because it's the variance of an energy. But in non-equilibrium, it's about heat, which is correlated with occupation. But you see, in non-equilibrium, you can have population inversion. That is what Escher is showing us. You can have that even though you're higher, the water flows to you. Instead, so you're lowering your energy, and to lower your energy, you need heat coming in. That's what happens in non-equilibrium, possibly. So you have this population inversion, namely the occupation of the higher energy levels is typical instead of that lower at low temperature. So that means that the occupation spectrum is no longer positively correlated with the quasi-potential. And that gives you the negativity. And especially at low temperature, this is prominent when beta is large. And that
And
I'm
you know,
sorry,
and you
but
know
we have to-
parameters that you have to tune to
I'm
avoid
very
this
sorry,
negativity.
but we have to go on.
yes,
We
sorry.
have we have to soon go to another speaker. If we have more questions, I didn't quite understand. Christian, did you get to all the end of your talk?
Well, I of course, the end of the talk is defined by 30 minutes, and by what I could say, it is a bit long, but I try to give at the end the basic ingredient of the mathematics, which is a solution of a Poisson equation in terms of mean first hitting times, which you have to evaluate for all these graphs at low temperature. What I did not say is, of course, that if you have special, the more edges you have, the easier it is for the third law to be satisfied. So on the complete graph and for bounded rates, the third law is always satisfied. So I mean, I could give you all kinds of corollaries, but I don't have time for that, I think.
If you stay with us, maybe we can go back to discussion after in the break.
Well, that's maybe possible, but if you have questions, you can always write me. I mean, would be very happy to explain more and privately explain to somebody or answer questions by email. I will be very happy to do that.
Thank you. You made a very educative talk.
Okay,
of course, it would be interesting to see the dependence on the graph structure.
Yes,
because in
true.
the equations there is absolutely no graph structure. And
Well,
another question.
Matrix
Another question would be about different scalings, because it seems when you approach zero, there are different scalings where you can see different behavior, but maybe it's only on the picture.
Okay.
Good. Okay, if anybody on Zoom
yeah, I mean, people
do we
can
have
write
any
me. I
question?
will be very happy.
I do have questions, but I will email them.
Okay, but be welcome. I mean, we can speak privately or via email as you wish.
Thank you.
Sure.
Thank you very much.